All things tech, all in one place. Tech Talks.
All right, today we're going to dig into the invisible world of our cellular network to figure out why those little signal bars on your phone can be, well, such liars. Okay, let's get into it. You know the feeling, right? You've got 5 perfect bars of signal, a full house, but that web page just spins and spins. A video refuses to load. It's one of the most frustrating things. So how can a perfect signal be so completely useless? The simple answer is, those bars, they're not telling you the whole story. Not even close. So here's the real secret. Your bars show you signal's strength, but what you actually care about, what gives you your speed, is signal quality. A strong signal is totally useless if it's packed with noise and interference. Think of it like being at a super loud concert. That's a lot of strength, but if you can't understand the person screaming right next to you over all the noise, that's terrible quality. To really get what's going on, we have to learn the language that our phones and the cell towers are speaking to each other. It's a whole conversation that isn't measured in simple bars, but in these specific technical metrics that give us a much, much clearer picture. Okay, so first up, we have this thing called RSSI. This is pretty much what your signal bars are based on. But here's the big catch. RSSI measures everything the antenna hears. The useful signal you want, sure, but also signals from other towers, Wi-Fi, microwave ovens, all the background electronic noise. So for modern networks, it's just a really rough number and honestly, not very helpful by itself. Now, a way better metric is something called RSRP. See, instead of measuring all that noise, RSRP measures only the power coming from the specific cell tower you're actually connected to. This gives you a pure, clean measurement of the signal's strength, without all the interference. This is our first really important number. But even a strong signal can be useless if it's just being drowned out, right? And that's where our second key metric, SINR, comes in. This measures your good, useful signal against all the background interference and noise. A high SINR means your signal is crystal clear. A low SINR means it's getting lost in the static. So what do good numbers actually look like? Well, for RSRP, if you see anything around negative 80 dBm or better, meaning closer to 0, that's excellent. Once you start dipping below negative 100 dBm, you are getting really close to losing that connection entirely. And for quality, we're looking at SINR, where a bigger number is always better. If you have a value over 20, that's fantastic. As it drops down towards 0, things get pretty shaky. And if it's a negative number, well, that means the noise is literally stronger than the signal. Your connection is in some serious trouble at that point.
Quick pause. If you like what you see, hit like and subscribe. Thanks for the support.
Okay, so we've talked about the signals themselves, but what about the actual hardware that's sending and receiving them? Antennas are absolutely critical, from the tiny ones inside your phone to those big ones on the towers, and they all work based on a principle that might actually surprise you. This is probably the biggest myth out there when it comes to antennas. High gain does not mean amplification. An antenna isn't a booster. It's not making the signal more powerful. See, gain doesn't create any new energy. It just takes the energy that's already there and redirects it. I love this analogy. Think of a radio signal like a bare light bulb. It's just radiating energy out in every direction. An antenna's gain is like the reflector and lens inside a flashlight. It doesn't make the bulb any brighter, right? It just gathers up all that scattered energy and focuses it into a tight, powerful beam that can travel way, way farther. That's gain. And that gives us 2 main kinds of antennas. You've got omnidirectional antennas, which are like that bare light bulb, great for covering a wide area, like your home Wi-Fi router. Then you have directional antennas, which are like the flashlight, that concentrate all their energy in one specific direction, which is perfect for creating long-distance links to a cell tower that's miles away. All right, so that signal gets picked up by the antenna, travels down the tower, but what is actually in those boring gray cabinets you see at the bottom? What's the machinery in there that powers our entire mobile world? Well, inside that box is what's called the base transceiver station, or BTS. This is basically the heart of the whole operation. Its key parts all work together. The transceiver sends and receives the signals. The power amplifier gives them a massive boost for the long journey to your phone, and other components manage all the traffic so multiple signals can use the same antenna without causing total chaos. So we've got the signal, the antennas, and the tower hardware. But if you're in a city, your phone can probably see dozens of towers all at once. How on earth does it pick just one? And how does the whole network not just collapse into total chaos? Well, it all comes down to a kind of secret handshake. And that handshake is the physical cell ID, or PCI. Every single cell sector has one. You can think of it like a unique name tag. Your phone isn't looking for Verizon or AT&T. It's looking for a very specific PCI to tell one tower's signal apart from all the others. Here's the crazy part. There aren't millions of these IDs. There are only 504 of them, total, from 0 to 503. Now, think about the tens of thousands of cell sites across the country. Yeah, you can see how this gets tricky. Those numbers have to be reused, and they have to be reused very carefully. And this is where the real genius comes in. If two nearby towers use PCIs that are too similar, their signals can actually clash and confuse your phone. So to stop this, network planners use these complex mathematical rules to make sure that any towers right next to each other have IDs that are different enough not to interfere. It is a constant, massive puzzle they have to solve every single day. Okay, so let's pull all of these different threads together now. We've looked at the signals, the antennas, the hardware in the tower, and the logic of the network. For your phone to give you that fast, reliable connection, all of these separate pieces have to perform this perfectly coordinated, invisible dance. So the main thing to take away from all this is that your connection is anything but simple. It is a constant, real-time negotiation between signal quality, antenna focus, the tower hardware, and all those network IDs. So next time you have full bars but super slow internet, you know what's happening. It just means one of the dancers in this invisible performance has tripped up. And that really leaves us with one big question for the future. This invisible dance is already mind-bogglingly complex. But with 5G and the Internet of Things, we're about to add billions of new devices to the dance floor. Cars, traffic lights, your refrigerator. How in the world is this intricate dance going to evolve to keep our hyper-connected future from just collapsing into digital noise?